Hello everyone, I am Yaman Sanger, a graduate student in the University of Wisconsin at Madison. I'm working with Professor Bhuvana Krishnaswamy at the W Connect lab, and I'll be presenting our work titled WiChronos today. In this work, we focus on the problem of scalability in a low power wide area network, also called as an LPWAN. So let's consider a sensor network deployed in a farm. You have thousands of sensors that are deployed at distances ranging in the order of kilometers, and each of these sensors communicates to a central gateway. Now, if we look at it closely, the sensors are buried under the soil, which means that replacing batteries is cumbersome, and so these nodes must last for years. They're deployed widely in the field, and they need to communicate to a central gateway over long distances. Sensors must also coexist with each other in the network. Now, these requirements of energy efficiency, long range, and large scale can be generalized to a majority of in situ monitoring applications, not just precision farming. The growing need for these LPWANs has resulted in a number of commercial solutions such as LoRa, Sigfox, and so on. Now, these state-of-the-art LPWANs have focused on low-power communication because radio is the bottleneck in power consumption of a sensor node. A typical sensor node consists of a sensor, a microcontroller, and a radio as shown in this block diagram. If we look at the current consumption of each of these components, we can see that the radio is in fact the power-hungry module. Therefore, wireless energy efficiency is the bottleneck for the battery life of these sensor nodes. Now, looking at the state of the art, a vast majority of low power communication algorithms have low range. So, for example, backscatter and RFIDs are in the lower left corner of being low power but also low range. On the other hand, the cellular networks, which give us longer range, are extremely power hungry. So these LPWAN solutions like LoRa, Sigfox, and NB-IoT have emerged as a compromise for both low power and long range, but then they're not particularly scalable. Now the size of the bubbles over here represents the scale of the technology. Monitoring applications require scalability to be able to support thousands of devices. So let's see why it is that they're not scalable in the next few slides. In this slide, the blue color represents control parameters, green is a desirable effect, and red is an undesirable effect. Now, LPWANs and other solutions for long-range communication operate at lower frequency bands and in narrow physical layer bandwidths, that is, the radio bandwidth in hertz. This is due to reduced noise flow and therefore improved signal-to-noise ratio at a lower bandwidth. So narrow bandwidth is needed for long range, and conversely, if the bandwidth is high, then the range goes down. Now, the downside to decreasing bandwidth is that the data rate reduces, and conversely, the data rate increases with increasing bandwidth. But the reduction in data rate increases the time on air, which is essentially the duration for which the radio must be on, and that impacts the battery life negatively. At the same time, the total time for which the channel is being utilized also increases, and so the probability that there may be a collision also goes up. Conversely, increasing bandwidth decreases the time on air, and in doing so, it helps achieve a better battery life and lower collisions. Now, what we can see clearly is that the requirements on the coexistence of our desired properties of low power, long range, and scalability is conflicting. And so while long range is achieved by operating in an ultra narrow bandwidth, that also increases the battery life and collisions. So the question is, how do we achieve all of these simultaneously? And our solution to this problem is an energy efficient time modulation for data transmission that we call WiChronos. What we propose is to encode data in the time difference between two symbols that we call start and stop. So in this illustration, I have a WiChronos transmitter connected to a soil moisture sensor that has recorded a data value of 83%, which means that 83 is the data that needs to be conveyed to the WiChronos receiver. Now to do so, the transmitter first sends a start message to the receiver. Upon sending this message, it triggers the timer on and starts counting at a predefined clock. The receiver receives the start message and upon doing so, starts counting precisely at the same clock as the transmitter. Once 83 clock cycles are up, the transmitter sends a stop message to the receiver. and the receiver, upon receiving the stop message, stops counting, and this count, which is 83 at the receiver 2, is the data that had to be transmitted. Time interval modulation, such as pulse position modulation, has been proven to be one of the most energy efficient in optical networks. But then adopting them for wireless networks is challenging, particularly in a wide area network. In this work, we design and prototype the start and stop symbols using commercial off-the-shelf components that have the three desired properties of LPWANs satisfied. In fact, there was a challenges paper in MobiCom called Communication Through Silence many years ago, and that served as a motivation for our work here. Now, before I get into more specifics about our implementation and prototype, let's briefly revisit our goals and how we achieve them. So the first goal that we have is energy efficiency. Majority of the existing modulation techniques, they have a transmitted packet which consists of a physical layer header followed by the payload. These header and data bits are all sent over the air, and the power consumption depends directly on their length. So the longer the message, the longer is the message duration, and hence more the power consumption. On the other hand, WiChronos sends a short start and stop message over the air. Active data transmission happens in the time elapsed between these messages. The entire transmitter module is maintained in deep sleep in that time frame. In other words, the transmit power consumption is a constant. It is irrespective of the message length. WiChronos in this way separates time on air from active transmission time. By choosing shorter anchor symbols and sleeping during active transmission time, WiChronos reduces the total energy consumption of the transmitter. The time on air is entirely a function of these start and stop symbols, which we will refer to as anchor symbols. Now, given the importance of these anchor symbols, it is crucial that they are designed optimally. So let's talk about that. While short anchor symbols are desired for energy efficiency, they are prone to losses and errors. Anchor symbols serve two purposes. One is to act as start or stop message, and the second is to uniquely identify the transmitter. Now, a very short anchor symbol is subject to being read as a false positive, and the probability of false positive of a frequency shift keying anchor symbol is what we have presented here. The higher the number of bits, the lower is the chance for them to be read erroneously. For any given modulation, though, we can also plot the probability of symbol error. And so for narrowband FSK, the plot looks like this. And what we see here is more the number of bits, higher is the probability of a bit error in the anchor symbol. So to recap, shorter anchor symbols are better for energy efficiency and bit errors, and longer ones are better to reduce the probability of false positives. So we define the optimal length to be the shortest length that enables reliable decoding at the receiver. In other words, the shortest number of bits that have a low false positive rate as well as a low bit error rate. And a visual inspection shows that a length of something around 10 to 12 bits, as is highlighted here, hits the sweet spot where the probability of symbol error and false positives are both fairly low. So let's move on to the next desirable feature, which is long range. Now, we saw earlier that a lower bandwidth and sub-gigahertz band operation is typically used for long-range deployments. Let us consider the impact of bandwidth on an FSK modulated signal. For a given received power, the noise flow decreases with the bandwidth, as is evident in this graph. Since the signal-to-noise ratio is inversely proportional to the noise flow, the SNR decreases with increasing bandwidth, and therefore at lower bandwidth we see higher SNR, and we can hence reach much longer distances. Following the same reasoning, WiChronos also operates at narrow bandwidths. The next desirable feature that we have is scalability. Now, due to simplicity of implementation and its energy efficiency, Aloha is the most common MAC protocol used in LPWANs. But then the collision performance of Aloha suffers with increasing network traffic. Collisions occur when one sender begins transmission during an ongoing transmission. So for instance, While sender 1 is transmitting its payload, sender 2 begins transmission while sender 1 wasn't done yet, and that causes a collision. The data from both the senders is now lost, and since the headers and data occupy channel for a long time, the probability of a collision happening are also high. But then when we look at WiChronos, sender 1 starts its start anchor whenever it's ready and then goes to sleep while data is actively being sent. Sender 2 then uses the channel to send its start signal and goes to sleep as well. It wakes up, sends a stop signal, and then completes its transmission. Eventually, sender 2 also transmits its stop anchor, and the fact that these anchor symbols are short and that the sleep time in between them is high in comparison, it is possible for them to be interleaved. So WiChronos is able to utilize the channel far more efficiently because of its lower time on air that reduces collisions. So just to recap, WiChronos utilizes an ultra narrow band to attain long range. While that has a negative impact on collisions and range, that effect is very small compared to the reduction in time on air by using anchor symbols and maintaining the devices in sleep mode during active data transmission. This helps us reduce the time on air significantly, increasing the battery life and reducing the rate of collisions. So now that we understand how WiChronos achieves these desired properties, let's talk about the implementation and the sources of error as well as payload accuracy. I will refer to the start and stop anchor symbols as preamble and postamble in the implementation. As I stated before, we use off-the-shelf components to prototype WiChronos. Links NT transceivers are used as transmitters and receivers, and the low power line of microcontrollers from TI in the MSP series is used to control these transceivers. We operate at a center frequency of 915 megahertz with a bandwidth of 100 kilohertz, and that was the minimum that Links could give us. The transmit power is 13.5 dBm, which again is maximum possible by Links NT, the transceiver that we've used. These bandwidth and transmit power numbers limit our maximum achievable range to about 904 meters, and that is a limitation of the hardware that is being used here to prototype, not of the algorithm itself. Now, this is an illustration of the current consumption of a WiChronos transmitter. The sensor data is read and digitized, upon which the radio is turned on to send a preamble. The preamble consists of 4 bits of alternating zeros and ones, followed by 12 bits to ask the reader to start counting as well as identify the sender. Each sender is assigned a unique preamble and postamble. The radio is turned off as soon as the preamble is sent, and the microcontroller is put to sleep mode with the timer running in the background. The timer is set to count as many clock cycles as the data. So from the previous example, we had 83 as the data to be transmitted. And so 83, or a data number of clock cycles later, the timer triggers the microcontroller to turn on, which triggers the radio to turn on and ramp up. It is important that the radio is triggered only at the appropriate time and for the shortest period of time that is required. Controlling the radio on time is key to energy efficiency. So now that the radio is on, it sends the postamble, which also consists of 4 bits of alternating zeros and ones, followed by 12 bits to ask the reader to stop counting, as well as identify who the sender is along with the preamble. The microcontroller and radio are always in sleep mode anytime they're not really being used. Now I want to compare this to a conventional modulation. And as it's quite evident, a higher time on air means a longer time frame where a much larger current is being utilized. This image shows how WiChronos is effective in energy utilization. The current is high only when anchor symbols are being transmitted, and because of this low time on air, collisions are also very small. Now, it's evident that timing plays a very important role, and that the smallest inaccuracies or errors can lead to erroneous values. So next, I'll identify and understand the sources of these errors and take appropriate actions for their correction. Since information is being encoded in time, timing errors can exist because of a variability in the microcontroller processing time, as is shown here. There can also be a variability in the radio wake-up time. And a key insight to correcting these errors is that WiChronos does not require the transmitter and receiver to be synchronized because the information is encoded in the time difference between these symbols. Only the clock rate needs to be the same, not the absolute time itself. And so we offer a very simple means of correction. Rather than letting it be a variable, we enforce the microcontroller to wait for the upper bound of the wake up time every single time the radio is turned on. And so this ensures that the microcontroller waits for a fixed number of cycles each time. And then this number can simply be subtracted from the timer count at the receiver to obtain an accurate value of the intended payload. Now, if there's a difference in the clock rates, that could lead to a counting error as well, and this could be the effect of clock skew. So what we show here is a red clock that is slightly slower, and a device that is using that particular clock will end up counting an extra cycle. In fact, the 32 kilohertz clock that we use is rated to have an accuracy of 30 ppm, which translates to the possibility of one single cycle error. And we correct for it by using redundancy in translating sensor data to a payload. So we employ redundancy by assigning consecutive data values to clock cycles separated by 3. For instance, if a sensor data of 50 is assigned to 50 clock cycles, it is possible for it to appear as 4950 or 51 clock cycles at the receiver. We map all of these clock cycles, 4950 and 51, to the very same sensor data of 50. Finally, there can also be bit errors in the anchor symbol, or a part of the whole of the anchor symbol could be lost. We employ a stateful receiver which keeps track of the last received anchor symbol as to whether it was a preamble or a postamble. If the postamble was lost and the receiver receives 2 consecutive preambles, the receiver will simply ignore the timer and restart it, and in doing so, it'll ignore the previous payload, which essentially got lost. The receiver also maintains an upper bound on the timer value, and when the timer exceeds it, the receiver understands that an anchor symbol was lost, and it stops and resets the timer whenever something like that happens. Unique preamble and postamble values are assigned to all the transmitters to make sure that the receiver can keep track of them appropriately. Our experimental verification was done both indoors and outdoors, particularly for longer ranges. And this image shows precisely the location of our experiment, which ranges from busy roads to sidewalks and bike paths going through the woods. Our evaluations showcase how our prototype performs better than the state of the art. We calculated the battery life achievable for a small 250 milliampere hour 3.3 volt coin cell battery from the experimental values of current consumption of our prototype and of LoRa, and we used current numbers from the datasheet for Sigfox. WiChronos achieves a battery life of 10 years compared to LoRa, which is between 5 and 7 years, and Sigfox, which is less than a year. And this is due to the reduced time on air owing to short anchor symbols. Whatever be the size of the payload, the battery life of WiChronos remains the same because the energy consumption depends only on anchor symbols. Longer payloads reduce the battery life of all the other techniques significantly. The next evaluation I have is of the symbol error rate and payload error rate. For all the experiments we conducted, WiChronos was able to correct for all timing errors in the payload with an accuracy of 100%. This shows that our proposed correction mechanisms of using the upper bound for hardware variables and redundancy to correct for clock skew indeed works as we expect them to. When there were symbol errors though, the anchor symbols were ignored, so this 100% correctness is for timing errors when there was no symbol error. The symbol errors are a part of the symbol error rate that has been plotted here. Having talked about the energy efficiency and range, let's talk about scale as well. We define the network goodput as the total number of successful data bits transmitted in the network in a given duration. The goodput increases with traffic initially because of a larger volume of data, but then it peaks at a point and then starts reducing because collisions dominate and reduce the total number of successful transmissions, reducing the goodput. WiChronos performs 3.5 times better than LoRa in a network of 1000 nodes, and this is due to the reduced time in air as well as reduced data rate, which allows interleaving the anchor symbols during active data transmission. In conclusion, we proposed and prototyped a time modulation for energy efficient, long range, and scalable networks called WiChronos that achieves a 60% improvement in battery life and allows 1000 nodes to coexist with less than 5% collision probability. This was just the first step though. There's a lot of future work in terms of machine learning for optimal encoding of payload to clock cycles. Reduction in collisions is possible through FDMA or CDMA with Aloha. anchor symbol design can also take care of more research. I do appreciate you all watching this, and I'll be happy to answer any questions that you may have. Have a great day, and thank you all.